So we're starting electrochemistry this morning, and the cool thing about electrochemistry is um, obviously we get to work in kind of the realm of electricity and chemical reactions, but on a different kind of note, one thing that we'll see with electrochemistry is that it is in a lot of ways just an extension of what we just did. Um, by taking the concept of Gibbs free energy and the idea of energy output for a spontaneous reaction and turning that into something more profound in the sense that we'll be using that energy to actually do work. And the work that we'll be doing here is electrical work. So the the balance of things, we're going to basically cut this chapter in half. We're going to do the first four sections this morning. We're going to do the last four sections on Monday. And if you look at the titles here, the first four sections are things that, well, at least we've seen parts of before. So we're going to spend our first lecture time here kind of going back and trying to remember some things from chapter 5 when we looked at redox reactions and the movement of electrons and defining oxidation and reduction and oxidizing agents and reducing agents. And then in our second set, we will talk about how to kind of take that information and use it to start to predict and apply to batteries, voltaic cells. So what we need to start with this morning then is we need to go back in time a little bit and rehash some stuff from chapter 5. Chapter 5 was kind of the pivotal chapter in Chem 105 because in that chapter you had the majority of your proficiencies coming to light. And what we want to focus on here, at least initially, is we want to look at the idea of the oxidation number. And just as a couple of reminders, oxidation numbers are not the same thing as ionic charges or formal charges. What we're looking at with oxidation numbers is what we're looking at is kind of the state of affairs that it is in. So if I were to pluck this atom out of this molecule or out of this ion, what charge would it have based upon the environment that it's in currently? And the reason oxidation numbers are important is because they're going to help us to see how electrons are moving in a chemical reaction. So just to, again, rehash some old things, you might remember that oxidation numbers were governed by a couple of guidelines, some sets of rules. First of all, if I add together all of the individual oxidation numbers of a compound or of a molecule, an ion, the sum of all of those oxidation numbers has to equal the total charge. That's first and foremost the key rule. And what this means is that if I have substances, elements, that are in their natural atomic or molecular state, their oxidation state is going to be 0. Doesn't matter if they are atomic samples like helium or individual atoms of carbon, or if they're in more complex molecular forms like P4 for phosphorus, or I2 for iodine, or even C60 for a particular form of carbon. If they're in an elemental state, their oxidation number is 0. If they're individual monatomic ions, then their charge is their oxidation state. And then to kind of help us figure out the rest, we need to take a key look at some common states. So for example, if I have fluorine, fluorine is going to be -1 anytime it is bonded to anything else. Hydrogen. If hydrogen is bonded to a nonmetal, it's going to be +1. Oxygen. If it's bonded to anything other than fluorine, it's -2, unless it's bonded to itself, and then it's either -1 in the case of peroxide or 0 in its elemental state. So just as a review, let's just kind of go through and talk about how to do these kinds of problems and kind of get back into the swing of looking at things from a charge standpoint. So for the first couple here, anytime that we see anything that is ionic in nature, so this is copper 2 chromate, the first thing that we're going to do is we're going to separate it into its ions, because an ionic compound like this would exist as individual ions that are arranged together. And so if I look at it from that perspective, then the copper 2 is a monatomic ion, so its state is +2. For the chromate, it's a polyatomic ion. I'm going to need to break it apart. The chromium plus 4 times the oxygen has to equal the total charge of -2. Now, if I go back to my guidelines here, I know that covalent compounds, including polyatomic ions that contain oxygen, are going to have oxygen at -2. So chromium plus 4 times -2 is equal to -2. Chromium minus 8 is equal to -2. So the chromium must be +6. And so the oxidation states are +2 for copper, +6 for chromium, and -2 for the oxygen. If I add all of those together, +2 and +6 is +8. And 4 oxygens times -2 each is -8. +8 and the -8 cancel. That's how I have a neutral compound in the copper 2 chromate. We can apply the same kind of logic, the same kind of rules to any ionic compound. So in the case of magnesium oxide, I would just split it apart. I know I have the magnesium ion, which based off of the periodic table, I know is a +2. And I have the oxide ion, which based on the periodic table is a -2. So the oxidation state for magnesium is +2. Oxidation state for the oxygen is -2. That one's relatively simple, straightforward. Now for covalent compounds like these next two, I don't have ions to split it apart. I can't break it down according to cation versus anion kind of lines. But I can do the same kind of thing that I did up here, where I can break down the hydrazine here into, I have 2 nitrogens and 4 hydrogens. And the total charge for that will be 0 because overall there is no charge on this molecule. Here's where that second guideline would come up. Hydrogen is +1 in covalent compounds. So hydrogen's +1. So I can rewrite this. 2 nitrogen plus 4 times +1 is 0. 2 nitrogen plus 4 is 0. And if I start doing all the algebra, subtract the 4s, divide by the 2's, I get nitrogen at -2. So the nitrogen is a -2 charge, the hydrogen's a +1 charge. Does that make sense? 2 -2's is -4. 4 +1's is +4. The -4 and the +4 cancel out. I end up with a neutral molecule. In the case of phosphorus trichloride, I'm going to set up a similar kind of calculation. Phosphorus and 3-chlorine total out to 0. Okay. Here's where these guidelines, well, hold on a second. I don't have anything for phosphorus. I don't have anything for chlorine. How do I go about this? Well, this third bullet point gives us a clue. Main group monatomic ions retain their charge, but here's the problem. Phosphorus, its normal charge is -3. Chlorine's normal charge is -1. If I put all of that together, I get -6. That's not right. So how do I choose which one ends up being negative? This is where knowing something about electronegativity becomes a thing. So I can go to the periodic table and I can say, okay, well, which one is more likely to be negative? And so I look at the periodic table and I see that chlorine is much more electronegative than phosphorus based on its position. Chlorine is going to be the more likely negative charge, so we're going to give it its negative charge. So phosphorus +3 -1's is 0. Phosphorus -3 is equal to 0, so phosphorus must be +3. And so if we get into a situation like that, that's the logic that we would use to determine which one's negative and which one's positive. We default to electronegativity. Electronegativity tells us which one is going to be the more stable negative, and we go from there. So again, nothing new here, just different. Kind of rehashing some old stuff. All right, any questions so far? Okay, so let's come back then to redox reactions. With redox reactions, what we saw is circumstances where the oxidation states are changing as we go from reactant to product. And there are two processes that take place here simultaneously. Oxidation, the process of losing electrons. In the process of losing electrons, the oxidation number gets bigger, more positive, because it's losing negatives. And reduction, the gain of electrons, where something is adding more electrons, its oxidation number is getting more negative, which means it's going down. Now, if you remember back to Chem 105, we talked about both of these processes through one of these two mnemonic devices. Leoger, loss of electrons is oxidation. Gain of electrons is reduction. Leo the lion goes grrr. Or we talked about through the template of oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. What we also talked about in Chem 105 was the idea of oxidizing and reducing agents. That is, substances that are particularly good at either stripping electrons away from something else, in the case of an oxidizing agent, or particularly good at taking electrons away, or um, in other words, giving away those electrons in the reducing agent. And what we have to understand and remember is that this is a paired process. You cannot have oxidation without reduction. You cannot have reduction without oxidation. You have to have both at the same time. And in the process, whatever is being done usually comes with some kind of consequence. So if I'm looking at the oxidizing agent, which is really good at stripping electrons, I know that those electrons are going to go into that oxidizing agent in some kind of way. Something's getting reduced inside of that. And we can usually tell good oxidizing agents because they have good high oxidizing states. So if I look at my chemical formulas and I see that through oxidation numbers, I've got something that's got a +6 or a +7 or a +5 as an oxidation state, I know it's going to be a pretty good oxidizing agent. Because that high level of positivity is just begging for electrons. Reducing agents are a little bit harder to spot because sometimes they have extra electrons, sometimes they just have lower, less positive oxidation states. Now, one thing that we did not talk about in Chem 105 is we never asked you to actually balance these redox reactions. The reason we never asked you to balance them is partly because, well, one, it's difficult, and two, there was really no need or application for it for what we were trying to do. It was merely good enough at the time for us to just have you recognize when oxidation and reduction were occurring and not necessarily focus on the nuts and bolts of the hows and whys. We weren't getting that deep into solutions. And the primary application for doing this kind of balancing is electrochemistry. And we weren't going to get into all that thermodynamic stuff in Chem 105 anyway. But we did talk about net ionic equations a lot in Chem 105. And redox reactions are often given in their net ionic forms primarily because it's easier to view them that way. Redox reactions can often get pretty complicated, where we end up seeing that some redox reactions occur only in acid, some redox reactions occur only in base, and because of that, we end up having reactions where we've got hydrogen ions or hydroxide ions or water molecules that are just kind of messing around in the entire scope of things. And you wouldn't have thought to put them there in the first place. So because of this, redox reactions can rarely be balanced by inspection. The inspection technique was the technique that we used pretty much throughout Chem 105. Once you got past the need to draw a line down the middle, count up all the atoms on each side, you started to balance by inspection. Okay, I need 3 aluminum, so I'll put a 3 over here. And I need 2 sulfates, so I'll put a 2 over here. That method rarely works with redox reactions. One of the reasons it does not work is because with redox reactions in this net ionic form, we have charges that we have to consider usually. And in 105, we focused mostly on the law of conservation of mass, the law of conservation of matter. We didn't really ever talk about charge balance. But charge balance is important too, because we need to have equal numbers of electrons on both sides as well. So this reaction involving osmium oxide and iron, make osmium and iron 2, it's not as easy as just balancing out the osmiums. I don't know where oxygen came from. The balanced equation is there on the bottom, where I've got 8 hydrogen ions and I've got 4 water molecules, and the reaction stoichiometry is actually 4-to-1 instead of 1-to-1, even though that looks like it should be 1-to-1 based off of the initial equation. There's a lot going on here. Turns out that this reaction only occurs in acidic solutions. How do we account for that? So there's a process that we use for balancing redox reactions. And the process itself is formulaic, but will take some practice to get used to. And so the process is this. The first thing that we do is we start to identify pairs. Now, we've already done this before. We talked about the idea of conjugate pairs, where we could identify an acid and a base that were different by just a hydrogen atom. It's kind of similar. In redox half reactions, what we're going to do is we're going to pick out the pairs. Okay, I had osmium in this molecule and osmium in this one. That's my pair. That's my half reaction. I'm going to build around it. And I had iron on one side and iron on the other. That's my other pair. I'm going to build around it. So when we talk about splitting into half reactions, that's what we're looking for. We're kind of taking the 2 pairs of things that have changed and creating their own reaction that we're going to balance individually, and then we'll put them back together at the end. So first thing that we do is we split it into half reactions. The second thing that we do is we balance out each half reaction and we add them together. Third thing that we do is we look at charge balancing. So we know that the oxidation reaction is going to lose electrons. We'll have to figure out how many electrons it loses. We know that the reduction reaction is going to gain electrons. We need to figure out how many electrons it gains. And then we need to make sure that the 2 match, that the number of electrons that are coming out equal the number of electrons that are going in. So we end up playing a game of lowest common multiple, usually to figure out the number that we need to multiply by. We put them together, and then what will often happen is that in the process of balancing each half reaction individually, we'll see that we end up having stuff on one side that's also on the other side. So we need to do some cancellation to simplify overall. So this technique hinges on being able to balance the half reactions. And so here's what we end up doing. It's a process. We go through this in this sequence. First, we balance anything that's not hydrogen or oxygen. We just do that simply with coefficients. So if I have 2 aluminum on one side and 1 on the other, I make the 2 on the other side with a coefficient. Second step, we balance any oxygens by using water. And then we balance hydrogen using hydrogen ions. So we're going to go off of the assumption that this reaction is being balanced in acid. And that's what we'll do for the reaction here. Now, if it's actually in base, all that we need to do is at the end, we just change it around. So however many waters were on the one side, we shift it over to the other side. We turn the hydrogen ions into hydroxide ions. But the last thing that we would do then is balance the charge by using electrons. So let's take a look at an example. So the first thing that we would do is we would split this into half reactions. The half reactions, well, I've got iodate ion and iodine. So that looks like a pair. Oops. And I've got chloride ion and chlorate ion. Again, the root is the same in terms of they both have chlorine. So that's going to be my other one. So for the first half reaction, I have the iodate ion that I am turning into iodine. So there's my first half reaction. What do? Well, first, I would need to balance everything that's not hydrogen or oxygen. I can see that I have two iodines here, but only one here. So I'm going to need two iodates to give me the two iodines that I need. That was step one. Step two is to balance the oxygens. To balance oxygens, I need to use water molecules on the opposite side. So I have 6 oxygens here that are unaccounted for. I'm going to need 6 water molecules to give me those 6 oxygens. Okay, that balances the oxygens, but now I have a hydrogen problem. I now have 12 hydrogens on the product side. I had no hydrogens on the reactant side. So I'm going to need to add 12 hydrogens, 12 hydrogen ions to make up the difference. Now for the charge evaluation, I've balanced everything atomically. I haven't balanced everything from charge. I need to look at each side of the equation. Total charge on the product side is 0 because none of the substances over there have any charges whatsoever. On this side, I've got 2 times -1, so I got -2, and I've got 12 plus 1. So the total charge on the reactant side is positive 10. Now, to balance the charge, I'm going to be adding electrons. Adding electrons is going to make one of the sides more negative. Which side of the equation should I add this to? Should I add electrons to the reactants, or should I add electrons to the products? To the reactants. How many should I add? 10. So by adding these 10 electrons, that cancels out the positive 10 charge. There is my balanced half reaction for the iodate half reaction in acid. Now, is this a reduction half reaction or is this an oxidation half reaction? How do you know? Okay, that's one way to do it. The other way, we can look at the reaction directly. Oxidation is loss, right? Is this reaction losing electrons? No. The reactants are gaining electrons. Gain of electrons is reduction. So I could identify it as reduction based off of that as well. So you assigned oxidation numbers, which is great. You didn't actually need to. So this is the reduction half reaction, which means that the other one has to be oxidation. And so I've got the chloride ion turning into chlorate. This time, chlorine is already balanced, so I don't need to do anything further. I have 3 oxygens, so I need 3 water molecules to balance it. And I have now 6 hydrogen atoms, so I'm going to need 6 hydrogen ions to balance that. From a charge standpoint, -1 charge on the reactant side, because only the chloride is charged. -1 plus 6 means +5 for the product side. So I know that I need to add electrons to the product. How many electrons do I need to add? Not 5. Yeah, 5 gets you to 0. We need to go all the way to -1. So it's going to be 6. Okay, so I've got my 2 balanced half reactions now. We're not done yet. To get this all the way, I need charge balance. So I need as many electrons leaving the chloride as are coming into the iodate. All right. Every cycle of chloride gives me 6 electrons. Every cycle of iodate needs 10. So this is where we have to play that lowest common multiple game. What is the lowest common multiple between 10 and 6? It's 30. Now, most of the time, what people will do is they will take those 2 electron numbers and multiply them together, and that will give them a common multiple, which is sometimes also the lowest one. If you do that, it works, but you're going to find that every single coefficient is reducible. And so you just want to keep that in mind. So lowest common multiple here is 30. So I need to multiply this top reaction by 3 and this bottom reaction by 5 to get to that. And so that means that our coefficients are going to change. So now that we've addressed that, we can add together the 2 equations. So on the reactant side, we would have 6 iodate and 36 hydrogen ions and 30 electrons and 5 chlorides and 15 waters. And on the product side, we would have 3 iodine and 18 water and 5 chlorate and 30 hydrogen ions and 30 electrons. Now, as we're writing this, as we're saying it out loud, pretty quickly we can see there's a lot of commonality on both sides. And so we need to get rid of some of that commonality. So the 30 electrons, obviously those cancel out. The hydrogens, I have 36 in the reactant and 30 in the product. So those 30 in the product don't go there. Take away the 30 from here, that leaves us just 6. And I have 15 water and 18 water on the product side. So those 15 waters go away, and that reduces the 18 down to 3. So rewriting, for acid solution, the balanced equation would be 6 iodate and 6 hydrogen ions and 5 chloride ions, becoming 3 iodine, 3 water, and 5 chlorate. That would be the acid solution. One very quick and easy way to check if you are on the right track is that, generally speaking, if you have charge balance, there's a really good chance you have atomic balance as well if you did all the preceding steps correctly. So I look at the charges. -6 plus 6 is 0. -5, so -5 is on the reactant side. 0, 0, -5 on the product side. The charges are balanced. Chances are pretty good that the rest of it's balanced as well. Could I double check? Yeah. I could look at it and say, okay, I've got 6 iodine and 6 iodine, 18 oxygen, and 3 plus 15 is 18 oxygen, 6 hydrogen, 5 chlorine. Yeah, I've got it all. But generally speaking, charge balance and atomic balance usually go hand in hand. And so if you have it charge balanced, you're going to have the rest. Now, how do I turn this into base? For base solution, you flip the hydrogen and the water, and you turn the hydrogens into hydroxides. So that would mean 6 iodate and 3 water and 5 chloride turn into 3 iodine, 6 hydroxide, and 5 chlorate. And again, you can check it with the charges. -6 from iodate plus -5 from chlorides, -11. So -11 on the reactant side, -6 from hydroxide, -5 from chlorate. So 6 and 5 is -11 as well. So I've got equal balance on both sides that way. All right. Questions with this example? All right, let's take a look at another example, just to get a little bit more practice here. Write a balanced net ionic equation describing the oxidation of iron 2 plus by oxygen gas in acidic solution. Okay, so to oxidize iron 2, the most common other ion of iron is iron 3 plus. So that would be 1/2 reaction there. The other half reaction would involve oxygen gas being turned into water, because that's what the problem tells us. Since this is occurring in acid, we don't need to convert it into base. We can just follow the acid protocol that we just did. And this one's considerably easier because it involves a whole lot less stuff going on. So for the first one, I've got iron 2 turning into iron 3. Already balanced from an iron standpoint. There is no oxygen, so I can skip that step with the water. There is no hydrogen, so I can skip that step with the hydrogen ions. I can go straight to charge. Total charge on this side is +2. Total charge on this side is +3. How do I balance out the charge? Where do I need to put the electrons and how many do I need? Okay, 1 electron to the product, that's correct. Okay, is this an oxidation or a reduction? This one's an oxidation. Again, the way that we can tell is the reaction is giving up electrons. Oxidation is loss of electrons. Okay, so our oxidation half reaction is balanced. Let's look at our reduction half reaction. I have nothing other than hydrogen and oxygen here. So I start by balancing the oxygen. For that, I need 2 waters. Now I would go about balancing the hydrogen. I need 4 hydrogens, so I'm going to add 4 hydrogen ions. And the reaction here, let's see, I've got a +4 charge over here and no charge over here. So I need to add 4 electrons to the oxygen to cancel out that charge and get them to match. Okay, so I've got both half reactions now. All that is missing is that I need to get them to match electronically. So 4 electrons are required by the oxygen half reaction. The iron half reaction only produces 1. So I'm going to need to multiply the top reaction by 4 so that the electron counts now match up. Now, here's one thing that you can start to do. If it is feasible and relatively easy for you to kind of pick out of your own handwriting here, places where you can see where there is cancellation to be had, you do not need to wait until you've added everything together to start canceling stuff out. So in the case of the electrons here, especially, it's easy to see. I've got 4 electrons as product, 4 electrons as reactant. Those are going to cancel out. And so I add them together now. I get 4 iron plus 2 ions reacting with oxygen and 4 hydrogen ions to make 4 iron 3 plus ions and 2 water molecules. That's my balanced reaction in acidic solution. Again, I can check just to be sure using the charges. Positive 8 plus 4 is positive 12. 4 times positive 3 is positive 12 plus 0 is positive 12. My equation is charge balanced, which means it's also highly likely that it's atomically balanced as well. All right, any questions? All right, let's go ahead and take a short break here. When we come back, we will cover the second half of today, which is talking about how we actually put this into action with voltaic cells. But this is a good time to kind of take a cut here. So let's come back at 11.